Hi, welcome. This is our journal club once again. I am Mike, the first year PhD student of Now Chia Lab. Chuyin.
Yeah, my name is Chuyin, and I'm also a PhD student at the same lab.
I'm Lipeng. I'm currently research assistant in the same lab.
Yep, great. So today, I will be the host, and the paper that we have brought here is, give me a second. It's called The Dimensions of Similarities, by Fred and Nave in 1950s. So it's a very long time ago. It may be one of the first paper that tried to create some sort of similarity rating networks when doing the psychophysics experiment. So let's begin. First of all, we need to understand similarity in different contexts of the psychological research. One of them, potentially, is how we perceptually organize object that we experience. For example, in the paper, if I can actually show it, it would be nice. Give me a second. Share screen. So one of the examples that the paper have given is that if the participants are presented with these X and O's, and they were asked to copy these X and O's, um, often they will group the X together more closely and the O together more closely, just during the process of copying. This seems to suggest that we are unconsciously grouping things that look similar together while separate them out from things that seems dissimilar. Another aspect related is how we cognitively associate objects and concepts. One example that is used is color. It was written that according to William James, that colors are not really considered to be real identities, but hope probably we have very different ideas in these days, especially in our lab, which we really use similarities when dealing with colors. Another potential way to consider similarity is in conditioning and inhibitions. So if you think about your conditioning, I don't know, a rat or maybe a mouse, um, if you use the same stimuli over and over again, then the mouse associated with a reward of some kind, and then you present it with a similar stimuli that is looks kind of roughly the same. You are expecting the mouse to display similar behaviors. And as you manipulate this similarity, you're making the stimuli more and more dissimilar from the trained stimuli. You would imagine that the mouse or the rats are less and less likely to make a response. This applies to inhibition as well as conditioning. Okay, so that's similarity in psychological research back in 1950s. Great. But what does the word similarity even means? What's the definition of similarities? Now, there seems to be two ways to consider similarities. One is to consider similarity based on the common elements between stimuli. So imagine two different stimuli, maybe two shapes. You could say that triangle and rectangle is kind of similar in the sense that one shares three angles and the other have four angles. While triangle is very different from a circle because a circle has zero angles. That's one way to consider it. We know that back in 1950s, they already know that this is not necessarily a good way to consider stimuli similarities. especially when dealing with complex natural stimuli. It's often very difficult to identify these common elements, and sometimes the combination of these common elements may lead to very different results. So it's probably not a good idea. A better way to consider similarity is to look at the stimuli dimensions. A noticeable example is Hall's invention of just noticeable difference. So you can imagine that, let's say there's a sun stimuli, and we have two dimensions, one is pitch, one is volume. You can imagine that two stimuli that are different in volume that are just noticeable for participant to be able to actually identify. Then that's a very interesting and novel way back in 1950s. But of course, now we know that it's very common practice to use just noticeable difference. So that's one way to consider similarities as well. And now, we have introduced some of the background to similarities, but it turns out that similarity can be very tricky when we are dealing with complex stimuli or naturalistic stimuli at the very least. So one central question is what happens when there are multiple complex dimensions? How do they combine to form a singular similarity ratings, a total similarity, if you will? Now, there are several interesting aspects regarding this question. The first is that it's often difficult to identify these dimensions with stimuli that we can smoothly manipulate. They are often intercorrelated, and it's very difficult to separate them and experiment them. Another aspect is how do these dimensions that we identified actually combine to form the final total similarities? One consideration is Richardson's Euclidean space. I'm not sure about the exact detail, but based on the description, he asked participants to identify, so he presented the participants with three colors and asked the participant to identify which pair is most similar in these three colors and which pair is most dissimilar in these three colors. And somehow they used a method similar to factor analysis to create a Euclidean color space based on this similarity. Well, based on this ordering of similarities. That's great, but the author of this paper pointed out that there is a fundamental problem with such a Euclidean approach, is that essentially the axis doesn't fundamentally matter. You can have any orthogonal axis you want. You can essentially get the same distance. So if you think about color, you think about axes like hues, luminosity, maybe the intensity of colors if you are using Munsell color space, as Richardson was using. So these three axes are supposed to be what determines each colors. But if you're using a Euclidean space, it can be other axes as well. It doesn't have to be these three axes. And it will give you essentially the same distance between each colors. Maybe we can discuss this point a bit further in the discussion. But another approach to the how to combine different dimensions is Landau's additive model, where you simply look at each dimensions and the numbers on each dimensions. You add them together, you form the total similarities. So that's quite convenient. This also means that each axes are actually very important. And depending on what axis you use, you may get very different results. Now, the actual experiment that they have done, now it's a 40-page paper. I only have 2 hours. I didn't read all of it. So I will just be talking about the first experiment. So in the first experiment, they showed participants several parallelograms, each with different stimuli dimensions. Maybe good to have a look. Is it? Oh, great. Let me scroll down to, yeah, experimental study. Okay. Now, unfortunately, the author did not give pictures of what these parallelogram looks like. So we have to use our imaginations here. There are 7 parallelograms that have been shown, each with different properties. We see that on the y-axis here, we have different size. On the x-axis here, we have different tilt. Tilt simply means the angle between the long side of this parallelogram and the short side, the angle in between. Now, there are a few special things, well, namely one special thing about this setup is that one of the parallelograms have different colors from the rest. It's the F here, which is why you see this little bracket, right? Now, with this 7 parallelogram, essentially the author showed the participant a pair chosen from these 7, a pair of them, and asked for a similarity rating on a 7-point Likert scale. They have exhaust all possibilities and they do it 3 times. They only use the result of the second and the third times because they use the first time as like a practice session. Then they applied a methodology, an analysis methodology called the graded dichotomies to calculate the psychological distance between each pairs using the ratings. Now, the author did not describe how it is done in this paper, but he did cite another paper. I have taken a short look, but I will not go into too much detail here. This is the graded dichotomies. Now, this is the result. The x value is after the graded dichotomies, the psychological distance between each pairs. Now we can see that in here, the author also have added these identical pairs in the hope of setting up a 0 point. And yeah, as the value suggests, that's where the participants are rating them to be exactly identical, hopefully. We may not be able to discuss in too much detail what this means, but essentially this is sort of an adjustment to the raw X score here. The author considered it to be a better representation of similarities. Now, let's get into the more interesting aspect of the results. This is a geometrical representation of each of the 7 parallelograms and their relationship to each other. It's very difficult to understand. But one interesting thing regarding this is that we can see there's this A here in a dotted line and A here. It seems that it turns out that the relationship between A and C, the participant considered them to be quite similar. And they consider the parallelogram B and C to be quite similar, but they consider A and B to be quite different from each other. It seems that based on their description, A, because of its tilt, is a mirror image of C, essentially, which explains why that A and C is rated to be very similar, while B and A are rated to be quite, sorry, does that make sense? No, it doesn't quite make sense. Let me try again. We see that on the tilt score, that A and C are quite different. There's a big difference based on fields, but their rating are very similar. Why is that? It's because A and C are essentially mirror image of each other. Maybe that explanation makes a bit more sense here. Now, just going back to what we mentioned previously, we talk about two different hypotheses. One is the Euclidean hypothesis. One is this additive hypothesis. So the author is trying to figure out which one is correct, which one isn't, based on what they got so far. And in the additive hypothesis, they are essentially hypothesizing that the additive sum of each dimension should add up to be essentially the same as the actual psychological distance between the stimuli. So if we quickly go back to the tilt and area graphs, we see that D, C, B, and A are supposed to be in the same area, but very different tilts. So the tilt is the same, areas are different. And we can imagine that the differences between, let's say, the rating of A and B and let's say A and C would be the result of the changes in area, hopefully. In this case, because of the A mirror image, that's not the case. Okay, let me see if I can explain this properly. So if you add up the unidimensional difference between A and B,
or A and G, because G unit dimension means that for one dimension in tail and area, A and G have different A and G differ in both the dimension. Then we add maybe A and B and the G and B together.
yes, actually, that's a
Sorry.
I think we're on the right track.
Oh, okay.
Just to rough say what I think this is the case. So so we are trying to find the relationship between A and G, let's say this. So we figure out the relationship between A and B, which only differs on tilt. And then we figure out the relationship between B and G, which differs only on the areas. Then we add them up. We add up the 1.23 and the 1.05 between B and G. So that should be our final total similarities. And in this case, the total similarity between A and G is 2.6. So we add up 1.23, we add up 1.05. The result should be 2.28, which is quite similar to 2.6. Okay, that makes more sense. Thank you. And this is what this graph essentially trying to show, right? The additive hypothesis say that the y-axis, the additive sum, should be the same as the actual differences. And this seems to be roughly the case, which is in support of the additive hypothesis. Now, there are a few more results. I didn't quite fully understand what this table means, what this graph means. So I think I will just end the introduction here right now. Yep. Are there any comments or things that you want to discuss based on what I've presented so far?
Okay. Yeah, I think that's quite good. Also, this graph I also not fully understand for that, but before this graph, the content you presented are very good. Yes, I mostly agree with you. And yeah.
What about you, Chuyin?
Well, honestly, regarding the meaning of this, yeah, I don't really understand or say agree with that 3.4, that parameter.
Uh,
Coming from table one, or
yeah.
to me it looks like that kind of number just came from triangle inequality.
Very interesting point.
So yeah, because I don't really understand how and why this 3.4 is roughly a constant. So what the following figures mean, like figure 3 and figure 5, um, are unclear to me as well. So yeah.
But even if we don't look at the constant, it essentially just raised the line by 3.4, right? Which the relationship describing is roughly the same. It will be not very be sorry, it will not be very nice in this case. Um, but it's not, you know, like too much of a problem, I don't think.
Maybe I should say something because recently we or I and now and answer are look into some dimension issue of the similarity rating. So one thing I want to mention is regarding multidimensional scaling, MDS. We usually put our stimuli into this 3-dimension or 2-dimensional space by MDS, like plotting high dimensional data to a lower dimension space, right? And then this process is using metric multidimensional scaling, which is assume or collapse this similarity rating to a Euclidean distance. So we are, when we are doing MDS, we made a very strong assumption that the psychological distance between this embedding, video, color is Euclidean distance. But but we think it is not the case. And this paper, as the first paper that look into dimensionality, on one hand, we don't need to look any paper that before this paper. On the other hand, this paper first proposed the psychological space or psychological distance. It is not Euclidean distance. We cannot make such assumption. Remember, the Euclidean distance have several axioms. One is additive, right? If we go back to figure 1, or maybe figure 2, yes, this one. The distance between B and C and the distance between A and B should, if we add them together, it should be the same as A and C, right? If the psychological distance is Euclidean distance. Another thing is the difference or similarity between A and B should be identical to B and A. That means that if we present similar in different order, the participant will give identical similarity rating. But this is not the case. So we have a very strong impression that the psychological distance or similarity, we cannot assume it in a Euclidean distance space. So that's why we are interested in this kind of paper. Yes, and the figure 2 indicating that Euclidean distance apparently is we cannot we cannot accept that hypothesis. So this author jump into another hypothesis, which is additive.
Wait, that's sorry, that's the distance from A to C equals to the sum of distance from A to B and B to C, an assumption of Euclidean distance.
Oh, no, it is the square root, like
Yeah,
this kind of thing.
I think
Oh, wait.
that's not. I don't think that's some. That's just one dimension. If we only have one dimension, then that must be true.
Oh,
But if we have multiple dimensions, Euclidean distance only say triangle inequality.
oh, can you explain it?
It's like just imagine a triangle. So an ABC forms form a triangle. Then the distance from A to C must be smaller than or equal to the sum of A to B and B to C.
Yeah, that's triangle inequality. Only this assumption in multidimensional space.
Yeah, no matter how many dimensions there are, as long as it's a distance, then we should have this triangle inequality.
Oh, okay.
Yeah, that's the other part of the color data, the color similarity data from our lab. Yeah. Um,
Yeah.
and yeah, that's yeah, the other side, the other part is the A to B. It's not B to A part. Yeah, yes. That one I more related to quantum cognition.
Yes, it's
Um,
asymmetric effect like
So
yeah.
Mike.
yeah, but I get that's the first paper. So it's understandable to assume that's a distance because it's like 70 years ago. Um, yeah, but it's quite it's a puzzling or I'm quite curious where this constant 3.4 is from. I'm kinda
It's an
because
empirical
there
one.
is a process of scaling.
No,
Yeah,
I think they just determine it arbitrarily by calculating
arbitrary.
or observation.
So
Yes, this is the paragraph.
Yeah, it's
If you are asking, can they justify this 3.43? I don't think they have a specific
yeah, that's the thing. And when they when they found such similar numbers, no matter 3.43, 3.47, they arbitrarily set 3.4. Yeah, it's
mm,
I'm very curious why they did that, but probably nowhere to find the answer. Yeah.
I think it may have something to do with the graded dichotomy method that they are using. So are we seeing a different paper now, or is it the same paper as before? Am I sharing this?
yes, you are sharing the new paper that
Yeah, yes.
Okay, great. So the same guy, I'm not sure how long ago, written this. It's his method, so he's using it, fine. But if we scroll down to the actual, yeah, so the step-by-step application section, Where is it? So it mentioned something about adding or subtracting a constant. But I use both percentage for each. Ah,
Additional constant maybe to make
Ah, okay.
Ah,
So there it is, right? An additional constant may be added.
added to the sum of interval between them.
but it's not quite the case here. So I'm not sure.
Mm,
Mhm.
I think it's mainly to prevent negative numbers, but in here they are creating negative numbers. So I'm not sure what's going on exactly.
A common arbitrary origin so that they will be comparable with one another. So the purpose is to make it comparable by adding one constant.
Seems to be the case, yes.
Mm.
And by the way, this is one of the worst methods I have seen. It's not good. Just use that score or something. Anyway.
Hey, why do you think it is the one of the worst method in work in terms?
So it's using a bad Z score. So essentially, how I will try to explain this without asking you to read everything. But so imagine in this case we have similarity data. It's an on Likert scale. We have 7 grades of similarities, from identical to very dissimilar. Now, this method essentially tells us that we should create these cutting points to create 2 categories. So let's, I need to, so let's say we cut in the middle. So we have maybe 4 that's similar, identical, almost identical, sort of identical, medium. We consider them to be one group, and the other very different, kind of different to be the other group. We separate them cut them into 2 parts.
Yeah.
And we repeat this process with different cutting points. So this time we have 4 and 3, maybe we have 1 and 6, maybe we have 2 and 5, maybe we have 3 and 4, so on and so forth. And then we find these values. We look at a table of normal curves. And we translate these percentage values of each into like on the normal curve into something similar to a Z-score.
Yeah.
And then we can add them together to form different kind of similarity rankings. I think that's the idea. I'm not sure if I've explained this well. I don't think I have.
Yeah, actually that makes sense because I haven't read this paper, this dichotomies.
Yeah. Let's just not worry about it. I don't like it. Maybe it turns out to be very clever, but yeah, I don't like it.
Okay.
Any other thing that we should cover with this paper?
I'm wondering regarding the quantum stuff, how what Chuyin mentions about the quantum distance or quantum projection to deal with psychological distance. Can you explain that?
Me or Mike?
Or I don't know, you?
From my side, just the order effect. Like the order effect, if we experimentally switch the order of stimuli, we get different readings, and we can feed the numbers into a quantum model, which I don't know about, the details. That's from a previous paper, and I think Elise paper, right? A few years ago, maybe last year or 2 years ago. That kind of no. I can't remember whose paper I did, but yeah, that's from a previous paper in our lab.
Okay.
Is it Apping 2023?
Yeah. Appin, yes, Appin, yes.
So yeah, essentially that they found for specific colors, there's an order effect. Depending on which color you ask first, participant can provide different, which color you show first, sorry, participant provide different similarity rate. And they build a quantum model around it, although I'm less familiar with the actual components of the model.
Okay. Yeah, thank you for clarifying.
Yeah. But in this case, we kind of see something almost quantum, right? We see that on the same physical dimension area with different tilt, despite the bigger differences in tilt, A and C are actually more similar comparing to, let's say, A and B. So it's kind of interesting, but I suppose the mirror image just sort of hand waves in the way that it may not actually be actually an order effect or quantum effect.
Yeah.
Well, actually, I was meant to mention this. Based on what the author has written so far, it seems that they have like what's the word? Kind of a desire to first find some kind of objective similarity dimensions before they investigate the subjective. It's kind of interesting, right? Because I feel like we are gradually deviating from trying to find these objective dimensions. Although I suppose we still use them in the sense of contrast or HSV value or so on and so forth. But we no longer sort of emphasize it a lot, seems to be the case.
Probably because our stimuli are getting hard to control.
Oh yeah, that's true. Like we change one dimension and all the other aspect will alter as well. Especially in natural C.
Yeah. Yes, and previously, people preferred such, say, easy to control stimuli, which might be complex, but easy to control. Like, maybe I can draw something.
Yeah, let me stop share.
No. Just using the notes.
Using the nodes. Give me a second. Let me put it back up. Can you draw? They're not seeing it if you are drawing.
Maybe something like this. Do you remember?
Oh,
That kind of stimuli. And it can vary size, direction, and
okay.
Uh,
I get it.
yeah, that kind of stimuli. And
sorry, is that motion?
no, not motion, just visual stimuli, or even see, and then some object maybe.
So the participant will ask to rate the similarity of the direction of this
No,
cursor.
no. That's yeah, not similarity rating, but to control the anyway, the point just they tend to use stimuli that are easy to control, but it can be very complex. Yeah.
Mm.
Yeah, I suppose the question really is what does complexity means in this case? Is it just a number of dimensions? Or is it something to do with how the dimensions are related to each other?
Mm, let me see.
If we are going to decide or determine the psychological distance, one way is like what this author do, picking some very simple stimuli and then identify two dimension. These two dimensions are very obvious, and then ask participant to rate the overall similarity between two stimuli. They assume that participant will only rate between two dimensions, then they can calculate the rating on each dimension. But the situation is phenomenal similarity is more complex than they imagine, because participant will also mirror the object, right? That leads to some unexpected kind of similarity rating. Then, if we present them with nature scene, with some complex color, with different shadow, gray, brightness, such kind of thing, we cannot identify this dimension beforehand. So in my emotion similarity videos task, initially, I found 6 dimension by multidimensional scaling technique, and then if I use other technique, it suddenly comes out that the dimension maybe is 1,000 or 100 to 1,000.
Yes.
But it is just because I'm not familiar with MDS, is there a way to determine which method is the best?
Um,
No.
no, and also
No.
this result or what I have contended is a little bit tentative. I'm not sure whether it is 100 to thousands dimension, but in Cohen and Keltner study, they found 27 distinct category of dimension.
Yeah, MDS is just a technique to visualize,
Mm.
so it cannot decide how many dimensions there are. Yeah.
I see.
The point is for those complex or holistic conscious experience like nature scene,
Yeah.
we cannot determine the dimension beforehand.
Yes. Similar situation happens to word embedding.
Mm.
And
Oh,
okay, for the audience, it creates multi-dimensional space for each word, and each word has a vector that represents its semantic meaning. So now it can have thousands of dimensions, as we can imagine. We have yeah, in terms of semantic meaning, there are a lot of potential dimensions. Yeah.
Only in
but
English, right? For each one word have 1,000 dimension.
No. The space can contain a lot of dimensions. Yeah.
Mm.
but
Mm,
what are these dimensions? Do they have like, real objective meanings, or are we forced to like make guesses on which one is which?
Mm,
I think it is very hard to give each dimension a meaningful interpretation.
yeah. Yes, yes.
Basically, this dimension or the embedding, this vector, this very long vector, is for computer or for machine to identify a specific word. For computer or for machine to understand that word, it is kind of like ID, the identity
Oh,
of
I
that
see.
word.
Mm, yeah, yeah.
Mm.
Uh,
Yeah,
right, right. This.
it is quite a old paper, a classic
Mm,
maybe. It is
Ah,
good as a starting point to learn dimension of similarity, but maybe it is out of date some method.
it's not a good starting paper because it's barely understandable. Sorry
well,
for
I
the
think
audience.
the difficulty for me is I barely know any of the citations there because that paper was written in 1950. Then it cited this paper even earlier, and then I don't know most of them. I just know Oscar and a few citations about word meaning. I know that part, but other citations, it's hardly for me to yeah to know it.
Yeah, and the paper doesn't tell you everything. It just sort of mentions it and then moves on, to
Yeah.
be honest. Uh,
Right.
well, are there any other point that we should cover, or is it is this it?
Okay. Okay.
So for today.
That's all for the day. Great. Well, thanks for coming. Perhaps next week we will have, or maybe the week after that, we will have a more interesting paper for you. But that's it for this time. Bye bye.